Hello class! In this video I would like to analyze some data for the ionization energy of elements. I would also like to relate that data to drawing the Bohr model and how we place those electrons in our energy levels. I'm going to focus on silicon today. So yes, I do have these three graphs, but I'm going to focus on the silicon. This is a graph of all of the ionization energies for all of the electrons in silicon. Now, what on earth is an ionization energy? Well, it's the amount of energy required to remove electrons from the atom. So here your y-axis is the ionization energy. We're looking at the energy. Here on your x-axis, these are the electrons that we are removing. So we notice in silicon, we've got some low energy here to remove these 4 electrons. They're kind of a group there. We get a little bit of energy here, so the 100 to the 1000 amount of energy to remove that set of electrons. And then we have these 2 electrons way up here that require more energy in order to be removed from our atom. Now, how can I relate this information to my Bohr model? Well, so far in the Bohr model, we know that we have our nucleus in the center. So if these are my Bohr model notes. Let's look at silicon. I know I have a nucleus in the very center of my atom, and this nucleus contains my protons and my neutrons. So my protons and neutrons are in my nucleus. And then I have these orbits of my electrons outside of my nucleus. This is the planetary model that Bohr discovered, or Bohr developed after his experiments. Now, in order to draw your Bohr model, let's review a little bit of information. So if this is silicon, let's determine our number of protons, neutrons, and electrons that I have in silicon. And this is an atom of silicon. Well, I didn't give you a particular mass number, so we're not quite sure which isotope this is. When I don't give you a mass number, let's go off of the mass number on the periodic table. So, if I look up silicon, silicon has a mass number of 28.09. Let's round that to a whole number, so that would be silicon 28. All right, your protons. That comes from your atomic number. This isn't quite the same periodic table that we use in class, but it still has all our main important information. For silicon, our atomic number is going to be the 14. That's our number of protons for silicon. Now, to find our neutrons, we take our mass number, 28, minus the number of protons, 14. So 28 minus 14 gives us 14. The reason why we subtract those two numbers is because your mass number, this 28, those are all of the particles in the nucleus, protons and neutrons. 28 total pieces, I know 14 of them are going to be protons, which means the rest are neutrons, which means I have 14 other particles, which are neutrons. Okay? And we did say that this was an atom. So if I have 14 protons, that means I have 14 electrons. Because atoms don't have any charge, they're neutral, so my number of protons balance out my number of neutrons. Excuse me, my number of protons balance out my number of electrons. So we have an equal balance of our positives and negatives. Now, we know our protons and our neutrons live in our nucleus. So they're going to be in the center. And we know our electrons are outside of our nucleus. But how many electrons fit in each of these rings? And that's the question we're trying to discover today. So, let me go back to this data table. This data is collected when scientists remove electrons. And they notice, let's look at these ones up here. These 2 electrons have really, really high energy. in order to remove them. It's a high ionization energy, over 1,000 electron volts to remove these electrons. While electrons are attracted to protons because they're opposite charge. So in order to have a huge amount of energy to remove these two electrons, it means they're really attracted to our nucleus. They're really attracted to our protons. So, these two electrons are located closest to our nucleus. I'm putting a 2 because it's a little easier to see the numbers. I could just as easily have put 2 little dots. Okay, so those are my 2 electrons that live really close to the nucleus, and I know they live close to the nucleus because they have so much energy required in order to remove them. Alright, so I've covered those 2. Next, we get a set of 1, 2, 3, 4, 5, 6, 7, 8 electrons. Kind of have a little lower energy. They're kind of this own little clump of 8 electrons. That's the amount that can fit into my next. These are called energy levels. So 1, 2, 3, 4, 5, 6, 7, 8. And they'd be a little bit more spread out than that. But for the sake of counting really easy, that's how I'm going to write my Bohr model. All right. There's 8, 9, 10 electrons. I've accounted for those. I still need to find a home for 1, 2, 3, 4 more electrons. So I need another orbital. And this can hold a maximum of 8. I only have 4 electrons to place, so my last 4 electrons are going to go in that last orbital. And if I count up all my electrons, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's the number that matches how many I should have. Each of these rings, each of these circles, they're called energy levels. Your first energy level is the one closest to the nucleus. It will always max out at 2 electrons. It can only hold 2 electrons. All of your other energy levels can max out at 8. So they can hold up to a total of 8 electrons. Now, we only have 4 electrons in this outer ring. That's fine. We don't exceed 8. That's the point. Okay, so let's try another example. Let's do nitrogen. First, count the number of protons, the number of neutrons, the number of electrons. Draw the Bohr model for nitrogen. Go ahead and pause the video and try that. Alright, welcome back. Let's see how you did. Nitrogen has a mass number of 14.01. So I'm going to say, I'm looking at nitrogen 14. Its atomic number is 7, so 7 protons. That also means we've got 7 electrons because we're looking at atoms. And then 14 as our mass number minus the 7 protons gives us 7 neutrons. So we've got 7 protons, 7 neutrons in our nucleus. That's my nucleus. My first energy level can hold 2 electrons. My second energy level can hold up to 8 electrons. But I don't need to go all the way up to 8 electrons. I only need 7. So here's 1, 2, which means the other 5 are going to end up in my second energy level. Let's try one more example and draw out calcium. Again, give me protons, neutrons, electrons. Go ahead and pause the video once you have those and the Bohr model drawn out. Alright, welcome back. Calcium on the periodic table has a mass of 40.08. I'm going to round that to a mass of 40. We've got an atomic number of 20, which means we've got 20 electrons. Our 40 as our mass number minus our 20 protons would give me 20 neutrons. So we've got our 20 protons, 20 neutrons. Those are present in my nucleus. I need to place 20 electrons. So my first energy level can hold up to a maximum of 2. My second energy level can hold a maximum of 8. So that gives me 8, 9, 10 electrons that I've placed. I still need 10 electrons to find a home. So I'm going to put another orbit, another energy level. This has a maximum of 8. All of your energy levels have a maximum of 8 except the one closest to the nucleus. Okay, so there's 8, 16, 17, 18. I still have 2 more electrons to place, so I'm going to put those in another ring, and I'm going to place my final 2 electrons. That would be my Bohr model for calcium. Now, if we look at the group, let's start here with silicon. If we look at the group that silicon is in, we call this group 1, our group 2, group 3, group 4, 4, 5, 6, 7, 8. Find silicon, we are in group 4. This is group 4, second column, second vertical column across. Now, we were in group 4. Something I want to point out is that we had 4 electrons in the outer energy level. In nitrogen, our nitrogen is in group 1, 2, 3, 4, 5. Group 5 for nitrogen. We have 5 electrons in that outer energy level. For calcium, calcium is in group 1, 2. Group 2, we have 2 electrons in that outer energy level. So, I'm going to call those valence electrons. Valence electrons are the electrons in the outermost energy level. These are the ones that are involved in bonding, either ionic bonding or covalent bonding, where we're sharing electrons or transferring electrons. The electrons in the outermost energy level and the number of valence electrons is the same as your group number. So your number of valence electrons is the same as the group number. And I'm using that pound sign or that hashtag sign to abbreviate my number. And again, your groups are your vertical columns, not your horizontal rows, but your vertical columns. One other observation I want to make about the periods now. So if we look at silicon and we count the row that it's in, this would be period 1, period 2, period 3. Silicon is in period 3. We have 1, 2, 3 rings, or we have 3 of those energy levels. If we look at nitrogen, nitrogen is in period 2. There are 2 rings, 1, 2. 2 of those energy levels. If we look at calcium, calcium 1, 2, 3 period 4, our 4th row down, calcium has 1, 2, 3, 4 energy levels. So your energy levels, and that's what I'm calling the orbits I've also caught myself calling them orbitals. You'll also hear the term shells. I've also said rings. Energy levels is the actual technical term. Shells, rings, orbits, that's kind of the other terms that you'll hear me say. These refer to your period number. So if you're in period 3, then you have 3 energy levels. If you're in period 7, you have 7 energy levels. Okay? Hope that was helpful for the Bohr model, and see you next time.